Good morning, everyone, and welcome to Bussmann University, a series of webcasts where experts from the Bussmann Series team cover today's most pressing overcurrent protection topics. My name is Shannon Stokes. I'll be your moderator for today's webcast. Today's webcast focuses on 2020 NEC code changes, and our speaker is Dan Neser, Senior Field Application Engineer for Eaton's Bussmann Series solutions. For more than 25 years, Dan has been providing technical guidance to consulting engineers, OEMs, electrical contractors, and industrial and electrical inspectors. He's sought after for his training expertise, particularly around SCCR. He participates in IEEE, NEMA, NFPA, UL, and IAEI panels and activities. Throughout this webcast, you are welcome to submit questions through your question and answer chat window, and we will do our best to answer them before the end of this webcast. In the next day or two, you'll receive an email with a link to watch this webcast and all of our previous webcasts on demand. Be sure to check out our upcoming webcasts as well. I will now turn it over to Dan. Dan?
Thanks, Shannon. Good morning, everyone. This is Dan Neser. Again, I'm the Senior Field Application Engineer for the Bussmann Division of Eaton. And I'm one of many, as you probably have seen on the previous webcasts we've done. There are other FAEs for Bussmann across the country. I happen to handle the Midwest area, so I'm based in St. Louis, Missouri. I cover Missouri, Iowa, Minnesota, North and South Dakota, Nebraska, and Kansas. So if you're in my territory, please feel free to reach out to me. I have my cell phone on there, and of course my email address. Just be careful when you spell my email. It's Neeser. So I'm available for any questions that might come as a result of this presentation. Of course, there is a Q&A where you can type questions in during this presentation, and I'll try to address them if I see them. Otherwise, they'll be addressed on the screen by Joe Shoemaker, who's also on the line with us. So I would also encourage, before we start, I would encourage all the attendees, not now, but at the conclusion of this presentation, to Google the Bussmann 2020 NEC code changes. That way you can get this document. It's available online. You can download it in a PDF format. The reason I say that is this document is very extensive in the number of code changes that we actually cover. When we look at my agenda, I'm only going to be focusing on 4 main areas. And those 4 areas deal with changes with regards to reconditioning equipment, service equipment, arc energy reduction, specifically with regards to fuses, and selective coordination is the last one. If you are registered for the May 20th session on SCCR and NEC requirements, I would imagine that they'll talk detailed about the changes that include 2020 changes to that topic. So let's start with the reconditioned equipment. So a little bit of history. Reconditioned equipment became a concern in the 2017 NEC when they added a section to 110.21a on equipment markings. And basically they added a section that said reconditioned equipment must be marked with the name, trademark, or other descriptive marking by which the organization responsible for reconditioning the electrical equipment can be identified, along with the date of reconditioning. Because what we see in the field very often is we see equipment that is being brought up back to operating condition, and because of the liability aspects, the original manufacturer does not want to have their company be responsible for that reconditioning. So if that equipment is brought back up to operating condition, then it has to be additionally, if you look at 110.21a, it'll say that reconditioned equipment must be identified as reconditioned. And it also will talk about some removals of listing marks we'll talk about in the 2020 code changes coming up in the next few slides. The 2017 change here, basically, it made them identify that we have to recondition, but it did not provide any guidance on what could or could not be reconditioned. So that really drove a lot of public inputs and comments for the 2020 NEC draft, second draft, first draft and second draft of the 2020 NEC. The primary guidelines that they used to identify what could and could not be reconditioned was the NEMA guidelines. And if you go to the Google and you can just type in NEMA guidelines on refurbished equipment, you'll get some guidelines on what can and cannot be reconditioned. And that was primarily used and what would be permitted per the 2020 code changes. So in 2020, we added a definition of recondition, and again, this probably will need some work, but as of the 2020, the definition for recondition is electromechanical systems, equipment, apparatus, or components that are restored to operating conditions. This process differs from normal servicing of equipment that remains within a facility or replacement of listed equipment on a one-for-one basis. And the real challenge here is, what is normal servicing? What is maintenance, for instance? And that hopefully will be further clarified in the next edition of the NEC. They also added an informational note that the term recondition is frequently referred to as rebuilt, refurbished, or remanufactured. If we look further into 110.21a2, you'll see the first two requirements that we've talked about previously that were in the 2017 code. They did add as mentioned, the removal of the original listing mark. Again, that's primarily to make sure that the original manufacturer is not responsible for the equipment after it's reconditioned. They also added in the exception that this refers to industrial occupancies, that the marking shall not be, the marking indicated in 110.21a2 shall not be required for equipment that is reconditioned by the owner or operator as part of a regular equipment maintenance program. So again, what we're talking about is it's not uncommon for an industrial facility to have equipment that perhaps is no longer operational, and they will do the bring that back to operation as part of their normal maintenance program. So that would not be considered reconditioned. If they're doing the work, they do not have to remove the original listing label and identify it as reconditioned. They also added two informational note. One about industry standards are available for application of reconditioned and refurbished equipment. So there are standards like Pearl that do provide some guidance for that. They had informational note 2 that talks sorry guys, I just had a little blip here of electricity. So I'm back on. Informational 2 discusses the term recondition may be interchangeable with the terms rebuilt, refurbished, or remanufactured. That was in there before. And the original listing mark may include the listing of the certifying body, not the entire label. And that's very important. Many manufacturer nameplates do not, many manufacturer nameplates have the UL symbol on that as well. And so what they're saying is you could just replace the original listing mark. Shannon, I've lost my internet here. I don't know. Can you advance to slide 8?
Sure. Yeah, for everyone who's live on this webcast, we do apologize. Here in St. Louis, a ripping thunderstorm has just opened up and released from the sky, so we're all experiencing some glitches with our electricity and our Wi-Fi. I'm now on slide 8, Dan.
Okay. And let's see, I'm going to pull up my. Okay. So what can be reconditioned? And this has been very common to recondition. So items that can be reconditioned are low and medium voltage power circuit breakers, high voltage circuit breakers, electromechanical protective relays and current transformers, switchboards and switchgear or sections of the switchboards and switchgear or sections of switchgear within the scope of Article 490. That refers to medium voltage equipment. If you do recondition this equipment, you are required to be listed or field labeled. So perhaps you could hire a third party to do a field evaluation of the equipment, and they would then label that as reconditioned. And there's some additional guidance with regards to fire and water damage, and that needs to be evaluated by the manufacturer or the testing laboratory to determine if reconditioning is possible. For instance, if we had a panel board that was in a flood, you'd need to contact the manufacturer to determine if it was possible to recondition that equipment. Okay, next slide. Okay. When we look at what is not permitted to be reconditioned, we have equipment that provides ground fault circuit interrupter protection for personnel. We have equipment that provides AFCI protection or GFPE protection, motor case circuit breakers, low voltage power breaker electronic trip units. So the low voltage and medium voltage power breakers can be reconditioned, but not their trip units. Medium voltage non-renewable fuses and fuse holders, and then a lot of devices such as receptacles, attachment plugs, luminaires, lamp holders. We mentioned panel boards already, other than replacement of panel board within the enclosure. And of course, some other critical systems such as fire pump controllers and transfer switches are not allowed to be reconditioned. Okay, moving on to service equipment.
Dan, there is a question. If a manufacturer reconditions its own equipment, do they have to mark it as well?
Well, I guess that's a great question. If the manufacturer is reconditioned, now I'm assuming that if that manufacturer comes out and does service on the equipment, where they're bringing it back to the original operating condition, I don't believe that would have to be marked as reconditioned. What are your thoughts on that, Joe? That's an interesting question.
I think the rules are a little bit different because they have access to all the original components that went in there. Presumably, if like Eaton Service Group goes and reservices equipment out there, they use all the same original components. So it would be a judgment call. I still think it should be marked, you know, when the date was serviced, but I'm not sure that it would require removing the original listing mark because all the components would fall under that original listing mark.
Okay, I certainly know that they're not allowed to modify the equipment. Like for instance, if you know you had a piece of equipment and you wanted, maybe you didn't have the proper short circuit current rating, and it was possible to modify that equipment so that you did have a proper SCCR, then you would not be able, you wouldn't be able to do that. A manufacturer couldn't come out there and then just relabel the equipment. So that is one thing I know would not be permitted, but I think you're right in this scenario. I think they have certain guidelines. Our engineering services group does that all the time. I don't think that'd be part of the normal maintenance, I believe, in my opinion. Okay, so now we're on. Yeah.
Motor control centers were not included on either list. And I can answer that one because that was Code Making Panel 11, which I'm on. And there was a lot of debate on whether or not to include those, but ultimately it wasn't, we didn't come to a consensus on whether they should or shouldn't. You will definitely see more input on those in the 2023 cycle. But if you're familiar with the code making process, it goes to the individual panels. And there's a lot of argument for whether it can be reconditioned safely or not safely. So it just comes down to the debate and how many votes there are. But you'll definitely see further modifications on that in the future codes.
Great, great. Thank you, Joe. All right, I'm back up and running, so I can advance the slides now. So I believe service equipment is showing at this time, correct?
Correct.
Okay, perfect. So let's move into service equipment. There's two major changes in service equipment. The first one deals with barriers, and this really is not so much a change, but more of an expansion to other types of equipment. So basically, if you look at the 2017 NEC and you went to Article 408.3A2, you would see language similar to this that required barriers for service panel boards, switchboards, and switchgear. And what we've done in the 2020 NEC is we've relocated that from Article 408 into Article 230, so now it applies to all service equipment. So no matter whether it's a panel board, switchboard, switchgear, it could be a disconnect switch, it could be an automatic transfer switch. Any type of equipment that is used as service equipment now must have barriers placed in service equipment such that no uninsulated, ungrounded service bus bar or service terminals is exposed to inadvertent contact by persons or maintenance equipment while servicing load termination. So we have a picture there on the right. So if I was to go into this, this appears to be perhaps a panel board, and that's the breaker there is the main panel board. What you can see there is they have some line side terminals covers to prevent any access to the line side terminals, and they also have some what we call like a boot, if you will, to prevent access, further access from accessing those service conductors. And the real drive for that was all about arc flash hazards and accidental shock, and being able to work on that equipment, because it is very common where you'd have to go into that service equipment and work on load terminations, and obviously you cannot do that, in many cases de-energize. So that adds an additional amount of protection. The other issue we have is the 6-circuit disconnect rule, and this has been in the code for many years. Basically, it allows you to have more than one service disconnect, up to 6, okay? And the idea for that is really what you're trying to do is you're trying to reduce cost. The problem with that is that when you have multiple service disconnects, there really is no easy way to work on this equipment. So, you know, they don't exclude the service equipment now, but they make it very difficult or provide very specific scenarios on what can be used when you have more than one service disconnect. And again, the idea is just to try to get you to have a single main disconnect, or prevent methods that are much safer needed and are permitted per Article 230 and Article 230.40. So basically you have 4 separate conditions. The first one is separate enclosures with a main service disconnecting means in each enclosure. The second one is a panel board with a main service disconnecting means in each panel board enclosure. So again, they're allowing you with separate services, but they're making sure that you have separate enclosures for each of those service disconnects. A switchboard where there is only one service disconnect in each separate vertical section, where there are barriers separating each vertical section. And again, there might be some interpretation needed to as what barrier is sufficient for that. And I'm going to show you some examples of what might be questionable with regards to compliance with option number 3. And then finally, option number 4, service disconnects and switchgear or metering centers where each disconnecting means is located in a separate compartment. And they do provide an informational note to that those metering centers are addressed in UL 67. The real challenge with this is, if you look in UL 67, there is no guidance for compartmentalizing meter centers, so it really becomes very difficult to do that. And then with regards to list item 1, they give an example of separate enclosures with a main service disconnect. Could be but not limited to motor control centers, fuse disconnects, circuit breaker enclosures, and transfer switches that are suitable for service equipment. So this is a very common scenario. I mentioned earlier about the meter centers. It was very common to perhaps just come into a pull section, a terminal, incoming terminal box pull section in the middle of that meter center, and then as you can see here, you have up to 6 tenant mains. And as mentioned, this would no longer be permitted. And really, if you look in UL 67, there's really no way from a UL perspective, to have guidance on how to compartmentalize those main tenant devices. So the rule for now is when it comes to meter centers, you really just need to have a single main for those meter centers. You cannot really purchase them with the compartmentalized construction. If we look at examples 1 and 2, here we have an example for separate enclosures on the left, and we come into a trough probably, and then we tap off into each service disconnect. Of course, those service disconnects would have to have those line side barriers. That's required per 230.40. And then we also look at this example of number 2. Here we come into a trough, and we go to 2 separate panel boards, each with their own service main. If we look at examples of separate vertical structures, I have two different examples here. Here we have a pull section, and we have service disconnect 1 and service disconnect 2, and they would need to be separated by a barrier. The real question is how is that barrier? Is it only, is it full height? Is it only where it's separated between SD1 and SD2, so maybe it would only be half the structure? Possibly. There's really no guidance on that. That's where the confusion would come in, and would highly recommend consulting with your manufacturers on how they do their barriers. And again, the idea is to prevent, if I was to work on the load side of service disconnect number 2, I don't want that arc propagating into service disconnect 1. And then on the second side, we have another example where we have basically the pull section in the middle, and then I branch off to each service disconnect. And again, full vertical barriers would be required. And the last condition would be for switchgear, and switchgear is very compartmentalized, so that is very easy to comply with. What you have here is that you have a pull section, and then we have 2 service disconnects. Those would be then via cross bus over to the, like SD1 would then have cross bus supplying over to FD1, SD2 would have cross bus supplying over to FD2. Many people often ask, why would you want to have more than one service disconnect? And there's a variety of reasons, obviously one being cost, as I mentioned earlier, but another reason is for the elimination of ground fault protection. If we look into Article 230.95 in the NEC, you'll find that we require ground fault protection if the ampacity of our circuit breaker or our fuses that can be installed are 1200 amps or higher. Then we need ground fault protection. So the challenge with that is when we have GFPE and we have critical systems such as an emergency system, the overcurrent devices on the emergency system must selectively coordinate with the normal source overcurrent devices. So, and I'm going to give you an example of this in the last section on selective coordination. But basically, when you put ground fault protection of the equipment on either the main or perhaps the second level feeder in the diagram shown here on the normal source, then what happens is that selective coordination becomes difficult to coordinate. So if I was to have ground fault protection on the service, I might be limited in the overcurrent device ampacity on the load side of the transfer switch and achieve selective coordination. So what you see on the right here is by creating multiple separate mains, which again is permitted per Article for Section 230.40 for critical systems, we are allowed to have a separate service overcurrent device supplying each of those critical systems. Joel, do we have any questions?
Nope.
Okay, great. Let's move on. So the next one is arc energy reduction, and this really is an interesting discussion. Arc energy reduction has been in the NEC. It's been a concern for the NEC, primarily for larger ampacity circuit breakers. And what we saw in the 2017 edition of the NEC was a requirement that addressed large ampacity fuses. And the guideline they decided to take for that was where fuses rated 1200 amps or higher are installed. So this does not apply to lower ampacity fuses. It's just to where we have those larger ampacity fuses, because what happens is when we have large ampacity, either fuses or circuit breakers for that matter, we might have available fault current and arcing current that is less than the current limiting threshold of the fuse or perhaps the instantaneous trip of the circuit breaker. And that can cause delayed tripping under fault conditions, which can be then result in high arc flash hazards. So what we're trying to do is address that issue, that if we have the case such that the available arcing current would result in delayed tripping, we want to add some sort of technology to provide faster clearing time and then obviously reduce the arc flash hazard. So the first thing you look at this is, well, if my fuse is 1,000 amps, do I have to worry about this condition? The answer is no. I do not have to worry about it. My fuse must be rated 1,200 amps or higher. Also notice this is a little bit, the wording is a little bit different than NEC 230.95 for ground fault protection of equipment, where it refers to the more of the switch size. So per 230.95, it says where the largest ampacity of the fuse could be installed. So if you had a 1,000 amp fuse and a 1,200 amp disconnect switch, you would have the requirement to meet the requirements for GFPE. However, you would not have to meet the requirement for 240.67. Also note that this applies, since we're in Article 240, this applies not only to service disconnects, but any overcurrent device, any fuse rated 12 amps or higher. Could be a feeder. It could be a feeder off of an alternate source of power. So if any fuses need to be addressed. And it also, I want to caution you, sometimes people would say, well, what if I had a 3,000 amp main with a 1,200 amp feeder? If I put arc energy reduction technology on the 3,000 amp main, does that then cover the 1,200 amp? And the answer to that is, the way it's worded right now, the answer is no. You'd have to look at each of them separately. So what's required? So if I do have fuses 1,200 amps or higher, and as you can see, the effective date is January 1, 2020, and they put that effective date in when they put it into the 2017 code because the solutions that they list there in Part B of 240.67 did not exist. So that gave manufacturers time to develop products that would comply if the fuse cannot provide the required clearing time. So as you know, though, however, if you're on the 2017 code, we're well past January 1, 2020. I'm sure everyone is thankful we're well past 2020 now, given the current situations we're dealing with. So this is a concern whether you're on the 2017 code or the 2020 code. It's just the amount of detail you have to provide, as you can see. So since the 2017 NEC, we've had to document the location of the fuses, okay? In the 2020 code, we added additional requirements to document that the method chosen to reduce the clearing time is set to operate at a value below the available arcing current. And for those of you who perhaps are not familiar with arc flash studies, you're probably very familiar with how to determine the available voltage fault current, but perhaps you're not as up to speed, if you will, on how to calculate the available arcing current. And I'm going to give you some tools on how to do that in my next couple slides. So we have to document that whatever we do, whether it's the fuse, okay, we either have to show that the fuse has a clearing time of 0.07 seconds, or we have to show that the options, differential relaying, energy reducing maintenance switching with local status indicator, energy reducing active arc flash mitigation system, or now in the 2020 NEC, we have the option for current limiting electronically actuated fuses. That those technology, if the fuse can't do it, that the different technologies in items 1 through 4, or perhaps new technology that would be permitted per list item 5, that will operate again within the arcing current. So if we look at this, how do we comply? Let's say we do have in our system, we have fuses that are 1,200 amps or higher. We first have to document the location of those. One method to do that would be to identify their location on the one-line diagram of your system. We then have to calculate the available fault current, and there's a variety of different ways you can do that. You can use programs, you can do hand calculations. Bussmann has a mobile app called FC2 that does available fault current calculations. Once I have that value, then I have to calculate the arcing current, and the only known method that I'm aware of today is to use IEEE 1584, or at least that's the very best method to use. Once we do find and calculate the arcing current, we then have to compare that to the total clearing time of the fuse. So as you can see here, we need to consult the time current curve, and I have an example of the time current curve shown there. So we basically would find the arcing current on the bottom axis, and then I would go up till I hit the fuse clearing time, and then I would proceed over to the left to determine the clearing time, and I'd need to be under or at 0.07 seconds or less. If you look in the 2020 code change document, we actually included a table that basically shows you for a specific type of fuse, this being the KTU, what would be the minimum arcing current such that we would guarantee clearing of 0.07 seconds. So for instance, if we had a 1200 amp KTU fuse, as long as my arcing current was 11.02 or higher, I do not need to go any further. The fuse will provide the required clearing time of 0.07 seconds or less, and I'm fine. However, if my arcing current was 10,000 amps, then I would need to investigate other types of technology and make sure that that will operate within the arcing current time. So how do we make this easier for you? The last thing we want to have people try to do is to, when they're not familiar with arcing current, is to try to calculate that. So what we did was we developed a program, and it's simply, if you just type in arc.bussmann.com, you will find our arc reduction calculator. We also do have an arcing current calculator. That's an older version of this. That version, however, only did the calculation of the arcing current, and it was the equations used were for the old version of IEEE 1584. The reason why you want to use this calculator is because it's based upon the revised equations in IEEE 1584 on the 2018 edition, and it also does the analysis of the time current curve to see if you need additional technology. So if you look at the different parameters here, I'm going to go right to the results because I think it's easier to see. If I look at the parameters here, you have the gap between the electrodes, and that depends upon the equipment types. For instance, if you had a molded, like a panel board, the gap you would choose would be 25. That's what I've selected here. So panel board, switchboards, the gap would be 25 millimeters. And if you look in the previous slide, I can go back to that real quickly. You'll see little informational notes, little question marks when a circle. If you hover over that, it'll give you guidance on what that gap means. The other thing you'll need to identify is the electrical configuration. And I mentioned that the new edition of 2018 creates new equations. And the biggest difference between the old equations and the new equations is the configuration of the electrodes. When we did the original testing for determining the arcing current equations for in the 1584 standard, we only considered a vertical orientation in an enclosure of those electrodes. In the next edition, we did additional testing where we did two additional orientations. One where the electrodes are still in the vertical position, but there is a barrier close to the end of the electrode that would then deflect that out more directly out the enclosure. And if you look at that VCBB will provide you with the highest arcing current available. If we look at the horizontal, that will provide you with the lowest arcing current. If we look at the horizontal configuration, where the bus electrodes basically face out of the enclosure, the arc is it does not deflect, it goes straight out, and that will give you the lowest arcing current. And that's very important. So if you want to consider worst case arcing current that would generate the lowest arcing current, you would pick the horizontal orientation. If you want to generate the highest arcing current, you would use the VCBB. So what we've done here is we selected the VCBB orientation. We gave an example here for a 40 volt system, a fault current of 45 KA, and again note the units there, that's 45 KA, not 45 amps. And then the fuse ampacity rating, which we allow you to select between 1200 amps, of course, where the requirement kicks in, and we only allow you to go up to 2500 amps, because what we found is, looking at time current curves and estimated arcing currents, if you get into 3000 amps or higher, you're going to have to use some sort of arc energy reduction technology. So 2500 amps is really the largest ampacity where we have the possibility that we may not have to provide arc energy reduction technology. And what you can see here, you see the corresponding arcing currents. We show a maximum and a minimum. The reason we show the minimum is if you look in IEEE 1584, it basically recommends taking 85% of the arcing current value to make sure that you're clearly within the time current curve for the required clearing time. And here we give you two options for this. We have our KRP-C 2500, which is our time delay class L, and we have a KTU 2500, which is our fast acting. And as you can see, provided you use the KTU 2500, you do not have to use any additional technology. If you use the KRP-C 2500, then you'd have to look at additional technology. So some options might be, and I have three examples here. The first option is the shunt trip switch with the arc energy reduction relay. That is what Eaton is currently offering. And basically the arc energy reduction relay provides a different curve for the lower values of overcurrent, as well as a maintenance mode, which would basically drop that to a rating of rated current of the capacity of the switch. So it'll provide that faster tripping time where needed. So the current would be detected by the arc flash relay and then tripped where appropriate. And then on the right, we have some high pressure contact switches from ABB/GE, and they basically have arc energy reduction technology in those high pressure contact switches. The last thing I want to cover with regards to arc energy reduction requirements is in the 2020 code, we now make you, not only do we make you document where the location is, we make you document that either the fuse or the technology will operate in the parameters needed. But we also now, in the 2020 edition, make you do performance testing. And this is an entirely new section. Don't let the crossed out text confuse you. If you look in your NEC book that you purchase, you won't see that crossed out text. But what happened is when they finished the second draft of the NEC, they realized that they had an error here. They required that you must primary current inject testing was the only option to test this equipment. And they realized that there are a variety of different reasons why you would not want to use primary current injection testing. So they basically did a TIA before the code even came out. They did a TIA that corrected this issue. And so now they basically require you to do testing of the arc energy reduction protection system, but you can use primary current injection where it makes sense or another approved method. And here's the real key thing here. It says this testing shall be conducted by a qualified person in accordance with manufacturer's instructions. And that's really what I want to draw to your attention. Whether it's no matter what type of technology you use, do definitely consult the manufacturer. The manufacturer will have, at least I can speak for Eaton, will have very detailed instructions on exactly step by step how to do the testing of the technology that you selected. And again, make sure that's a qualified person doing the testing. You know, if you have a person who typically does only residential electrical work, you probably don't want him doing this type of testing in a commercial or industrial facility. He probably is not qualified to do that testing. They also want to make sure that a written record of the testing shall be made and shall be available to the authority having jurisdiction. So if you don't have a document, it never happened, right? You have to have that written record. And then they offered an informational note on why we have the allowance for another approved method. And that's because some energy reduction protection systems cannot be tested using a test process of primary current injection due either to the protection method being damaged, such as the use of fuse technology. Perhaps you had a fuse limiter. Obviously, you don't want to run current through that. Prove the fuse does what you expect it to do, and then have to replace that fuse. Or because it is not the primary method of arc detection. So, for instance, maybe you have an arc flash relay, and you have that. You have the current aspect, but you also have the light aspect. So, you know, maybe you would not want to primary current injection test that type of technology either. Joe, any questions?
None at this time.
All right, fantastic. We'll move on to selective coordination. So what is selective coordination? Selective coordination is quite simply the ability to localize an overcurrent condition. So if I have selective coordination, as we see on the figure on the right, the overcurrent device nearest that overcurrent condition is the only one that operates. So that will clear the fault in this case before the upstream device operates. If we do not have selective coordination, the overcurrent device nearest the fault is not able to clear before the opening of the upstream device. And what happens then is when that upstream device opens, I lose power to unfaulted loads. And so the real reason why we have selective coordination is where we have the need for enhanced system reliability. That really is what drives the requirements where we have selective coordination. And there are several areas of code. We'll talk about several of them where we have requirements for selective coordination, but basically we're talking about critical systems. If we look at the definition of selective coordination to kind of help further clarify what we mean when we say and use the term selective coordination, the definition reads, it's simply the localization of an overcurrent condition to restrict outages to the circuit or equipment affected, accomplished by the selection and installation of overcurrent protective devices and their ratings and settings for the full range of available overcurrents from overload to the maximum available fault current. Now, they deleted the term maximum because in the 2020 code, as you'll learn next session most likely, they now have a definition of fault current and available fault current. And available fault current is simply the largest amount of current that can flow at a given point in your system. So we deleted the term maximum because now available fault current is defined as the maximum or the largest. And we also have to consider that for the full range of overcurrent device opening time. So, you know, for those of you who perhaps are new to selective coordination, when it comes to compliance, we have to consider all times and all currents. So up to the available fault current. So if you think time current curves are the only thing that might be required, that may not be the case. You also may need to consult manufacturer selective coordination tables or charts. One of the first sections where we have requirement for selective coordination is with multiple elevators. And the change here was they changed where it talks about where more than one driving machine disconnecting means is supplied by a single feeder. They changed that to the same source. And then it goes on to state that the overcurrent protected devices in each disconnecting means shall be selectively coordinated with any other supply side overcurrent devices. So the reason why they changed it to the same source is many would argue that the scenario I have right here where I have the main and two feeders, each feeder supplies an individual elevator, many people would say, well, that is not supplied by a single feeder. They would think that M1 is not considered a feeder, and that is not the case. M1 would be considered a feeder. It might be the service main, but it also is a feeder. Now, granted, there are special requirements for that because it is the service main, but essentially it supplies both elevators. The intent is that you do not want to have a fault on one elevator take out the upstream elevator, and there certainly is a possibility if B1 is not selectively coordinated with M1 and M1 does operate, I can take out elevator 2. They also added some wording about the selection process. Okay, so basically it has to be selected by a licensed professional engineer qualified person, and the selection and device settings must be documented. Codemaking Panel 12, who handles Article 620, felt it was important to further clarify that the device settings are also important to be documented, and that would be especially true when it comes to circuit breakers that have perhaps electronic trip units where you have multiple settings that are required to be set. They also put 2 exceptions in there that are similar to what's located in other parts of the code, other articles that require selective coordination. One thing I'll say here is that these are specific examples. The other sections of the code where selective coordination required really have this in a performance language, and I'll show you what that is in a couple of the next slides. Codemaking Panel 12 also went beyond what other codemaking panels have done, and they want to identify the enclosures by marking that we have selectively coordinated overcurrent devices in the field. So they require a field marking such as caution overcurrent devices in this enclosure are selectively coordinated, equivalent replacements and trip settings are required. So now be aware it says enclosures, right? So let's say that we have, obviously we have the enclosure where the elevator disconnect is located. So if we go back to that one line, elevator B1, that enclosure would need to have that field marking on it. But I would also consider that M1 and F1 also would need that marked as well because they are part of that system. Okay. When you look at one thing I should mention here, I don't know if I can advance this slide. I had a build in here. So if we go next, okay, here we go. So if the question comes, and the code only talks about the overcurrent device in B1 and upstream feeders, the question comes is, what if the fault is on the load side of F1? And if you look at the intent, I think you'd want to analyze the coordination, selective coordination of feeder 1 with M1, because we would not want a fault on the load side of F1 such that F1 would open, but it would not open fast enough before M1 would open as well. So this might be outside of what the actual text says, but I think it's certainly a consideration that needs to be done. Moving on to other critical systems that require selective coordination. Here we have one we go into Article 645, which covers critical operation data systems. So we're talking about data systems that are essential for national security or perhaps public safety. We just added some additional text that is, again, in other sections of the code where selective coordination is required. So this really is just having consistent language, and we just identified the importance of the selection being done by a qualified person and that it needs to be documented as we have in other sections of the code. When we look at fire pumps, it's very common to have a scenario where we have a multi-building campus and we have a feeder overcurrent device that supplies several other buildings' fire pumps. And this just basically states that those overcurrent devices must be selectively coordinated with all suppliers of overcurrent devices. So they kind of deviated from what we do for elevators by talking about just the disconnecting means for the fire pump. They now basically have this more as a system approach. And as you can see, they added the text about the requirement about the selection be done by a qualified person, and it must be documented. And we have that exception I mentioned earlier about the performance. So here we say selective coordination shall not be required between two overcurrent devices located in series if no loads are connected in parallel with a downstream device. So that's really the performance language. The other example in Article 620 gave more specific instances. This would be covered by this single performance exception. The real big change here occurred in Article 700, 701, and 708 for emergency systems, legally required standby systems in Article 700, and critical operation power systems in Article 708. What happened here is a little bit of history. I happened to sit on Code Making Panel 12, so I was involved in the discussion around this change here. And what had happened is in the public input stage, one of the panel members submitted a public input stating that whether or not you had to selectively coordinate with the normal source devices. And he put in two public inputs. One said you did not have to, the other said you do not have to. In the public input stage, we resolved his public input saying that the text is clear. It says that the emergency system overcurrent devices shall be selectively coordinated with all supply side overcurrent devices. All means all. So whether it's a normal supply side device or whether it's an emergency supply side device, selective coordination is required. In the public comment stage, we decided that although we don't want to change the wording in the parent text, we do think there might be some benefits to adding an informational note and a figure, and that's what we did here in the 2020 edition of the NEC. So it says, see informational note, figure 700.32 for an example of how all emergency system overcurrent devices, of how emergency system overcurrent devices must selectively coordinate with all supply side devices. So if we go to the figure, we basically gave a typical example of a emergency system. So let's say that device D supplies emergency loads, perhaps exit lighting. The emergency definitions by the scope of Article 700 include the devices that supply the emergency load all the way back to the alternate source for the emergency system. So what devices are classified as emergency system devices are devices D, C, F, and E. The normal source devices are B and A. Okay, they do supply emergency system loads, but they're not in the path to the alternate source of power. So what we clarified here was that the emergency system overcurrent devices must selectively coordinate with all supply side overcurrent devices, whether that is a normal supply side or an emergency supply side device. So if I look at device D, if there is a fault on the load side of device D must operate. However, devices C, F, E, B, or A do not selectively coordinate, or are required to not operate. If we look on the load side of device C must clear that fault, and device F, E, B, and A must not open. If we look at the fault on the load side of device F, device E must not open, device F must clear, device E must not open. However, if I go to the line side of the transfer switch on the normal side, if there's a fault on the load side of device B does not have to selectively coordinate with device A. Now, there are certainly benefits to having B selectively coordinate with A, but it's not required. And the idea is if the fault occurs on the load side of B and the line side of the transfer switch, then it really doesn't make a difference whether B opens or A opens or both of them open, because at that point in time we're switching to emergency to go to the alternate source. So that's really the clarification of what is required and what's not required. And often, for those of you who have done selective coordination studies in the past, you'll know that the the most challenging part of the coordination is often through the normal source. What makes selective coordination very challenging is fault current. If I have more fault current, then it can be more challenging for some types of recurrent devices. And the higher fault currents are going to come from the utility, and so that's why the real critical path there is to make sure we have selective coordination with the emergency system devices and the normal source devices. So wrapping up, what can you go or where can you go for resources? As you can see here, there's a variety of different resources that are available for you, starting off with the 2020 NEC changes document I mentioned at the beginning of the presentation. This is a very comprehensive look at a variety of different 2020 changes. You can download all of these documents from our website. We also have the 2017 SCR changes handbook and the 2017 code. The primary changes really dealt with SCCR. And when we talked, again, I want to promote the May 20th webinar. We're going to talk about 2017 and 2020 code changes that dealt with SCCR. If you want a free app to calculate fault currents, again, we talk about our fault current calculator, FC2. If you like information about all different types of overcurrent protection issues or topics, code compliance, we recommend our SPD Fuseology handbook. And if you want to learn just about fuses, the first section in that SPD handbook we also print by itself, and that's the Fuseology Technical Guide. So with that, I will turn it back over to Shannon to wrap up the presentation.
Thank you, Dan. Thank you so much. This is just a reminder that your registration into Bussmann University allows you access to all of these webcasts. So the first 3, and soon to be this one, are all available on demand. And the future ones you see here, you can join us live or wait for after live broadcast and watch those ones on demand as well. This concludes today's webcast. On behalf of the Bussmann Series team, thank you so much for your time. Have a wonderful rest of your day.